Oh, I think we have lots of review. I gave people their homework back. Some people may notice there's no pile in front of them. And that means that they better be turning in a lot of it today or it's basically worth 0. And let's see, we left off with basically only covering reactions. And what we should recognize, or hopefully this will jog memories loose, is that all of the reactions we're learning, there's only a couple of them that are really specific for the carbohydrates. And instead, they're all things that we've seen before. So if you can go back to the organic chemistry chapters, then hopefully what we're talking about today is sort of review. So our first set of reactions are going to be oxidations. And we're going to have a couple different types. We're going to have what we call mild oxidations, strong oxidations, and then we're going to have a couple named reactions that you guys already know. We'll show them to you as review and not spend too much time on them. So we've got mild and we've got strong. And what that really means is that we can oxidize things to different extents. And if we use a weak oxidizing agent, then we only oxidize one part of the molecule. And if we use a strong oxidizing agent, we oxidize the whole part of the molecule. So for a mild oxidation, the only thing we do is we turn an aldehyde into what? Into a what? Aldehydes go to carboxylic acids. And can we even oxidize ketones? No. So one of the ways that we can tell the difference between an aldose, which has an aldehyde, and a ketose, which has a ketone functional group, is simply trying to do a mild oxidation on them. If they oxidize, then they must have been an aldose, and if they don't oxidize, then they were a ketose. Now it's a little more complicated than that, because what else do we have on our carbohydrate molecules? They all have an aldehyde or a ketone, and then what other functional group? Well, no. What's the other functional group on a carbohydrate? When we draw one out, here, we'll just make one up. We'll make an easy one up because I'm lazy. We'll put all the OHs on the right side. And then see, here's our aldehyde functional group. What's the other functional group on these? Yeah, lots of OHs. Oh, that little yellow thing is annoying. Lots of OHs, right? So they all have alcohols. And what do we know happens if we oxidize an alcohol? If it's primary or secondary, it turns into an aldehyde or ketone. And if it's a tertiary, then we can't oxidize, right? So remember, all of that stuff we covered in the first 6 chapters on chemistry comes back to haunt you in all of these chapters. So try not. Well, basically, hopefully learning it the second or third time around will be the charm. So if I have strong oxidation, what that means is that I can oxidize my aldehydes to carboxylic acids, and I'm going to oxidize all my alcohol groups to I'm going to oxidize the end alcohol group into a carboxylic acid. So maybe I should put that this is the one on the end, or this is the primary alcohol. That's it. Now I'm going to draw 2 reactions. We're going to do this as a mild oxidation, and as a same molecule, we'll just do it as a strong oxidation. So in the first case, like I said, only the top functional group is changed. And so that goes from an aldehyde to a carboxylic acid. And you should also be familiar enough with these functional groups that you might see it drawn like that, or it's the same if that top is drawn like this, right? Meaning if they show the double bond to oxygen, or if they call it a COOH group, meaning that part should be the same. And then if I do it strong, what that means is that both ends of the molecule are turned into a carboxylic acid functional group. Otherwise, everything else stays the same. And then what we do to change the names is we call these onic acid and this is an uric acid. And what that really means is that depending upon what sugar we started with, we're going to change the ones we're going to put that ending on the name. Now, of course, I can't find my little sugar cheat sheet. What's the one that has all the OHs on the right-hand side? You should think I'd remember that because I always draw that one. It's easy. So this is diallose, right? What does the D part refer to? Yeah, this one right here, right? Not the bottom one, but the one that's chiral, the last chiral one, right? It's not really the bottom one. So you got to be specific with your language, right? I mean, I understand what you're saying probably when you say bottom OH, but is that really the bottom OH? No. Probably the best way to say it would be the OH on the chiral carbon furthest from the most oxidized end, meaning that's the technical definition, right? That covers all conditions. And so this would be D-alonic acid, and then this would be D-alaric acid. Okay, what's the opposite of, well, actually, let's just stay on with the oxidations. And we had two special oxidations that we know we can do. So special / named. And they're ones you've already seen before. We've got Phalings and Benedicts. And you guys remember which one that is? Yes, which one is which, though? Is Phalings and Benedicts silver or the copper? It's the copper. So if you guys remember the old reaction, we had an aldehyde plus 2Cu plus 2 ions plus NaOH. We oxidized it, and we get a carboxylic acid salt plus Cu2O plus H2O. And then remember that this was a pretty blue color, and it's aqueous, I guess we can put that. And this is a brick red precipitate. Well, because of that aldehyde group, we can also do this reaction with a carbohydrate. So the only thing that changes when you're writing out this reaction is you have to draw a big molecule, meaning you have to draw the big old carbohydrate instead of just our normal, aldehyde like that, right? So realize that these reactions aren't any different than what we've been doing. What changes is we've got bigger, uglier molecules to draw like the carbohydrates. So if we draw 2Cu plus 2, aqueous plus NaOH, and we oxidize that, then we're going to get the carboxylic acid salt. And then the whole rest of the molecule just stays the same. Oops. Plus Cu2O plus H2O. And I guess H2O is a liquid. We can put that down. And we know that that's a solid, so we can put that down too. So hopefully a review reaction. Hopefully it's one you already know. And the only thing that you have to refresh your brain on is that, oh yeah, carbohydrates can undergo this reaction too. Now I should point out that if you look up these named reactions in your book, one of the things I had mentioned sometimes is depending upon if they have that sodium hydroxide there, depends if you're going to make a carboxylic acid or a carboxylic acid salt. A lot of books will leave off that sodium hydroxide, and then when you draw the picture, it'll look like just a regular carboxylic acid is what they'll do. And so the reason that this is an oxidation reaction is that this molecule is oxidized, right? What's the sign of oxidation? We gained bonds to oxygen. This is a reduction. Now that's a little harder to tell that that's a reduction, because didn't that also gain a bond to oxygen? We actually have to go back to our real definition of what reduction means. What's the real definition? Meaning that idea of gaining and losing bonds to oxygen and hydrogen are signs that an oxidation reduction happened, but what's the real definition? not bonds to electrons, but electrons, right? So which one is which? Yes. So we should see that we gained electrons. And so notice that copper is missing 2 electrons here, right? That's what that +2 means. And that if I look at this molecule over here, that's really copper +1, oxygen -2, so each copper gained an electron. And so the copper specifically is what's being reduced in this reaction. It's going from Cu +2 to Cu +1, really. And so by following charges around, that's the best way to tell whether something's been oxidized or reduced. And we're going to focus on this a lot more the last, I'd say 2 weeks of class, where we're looking at the bioenergetics chapter, assuming we ever get there. No, we're on pace, kind of. We're a little behind. We may just skip some of the chapters in the past that I've skipped simply because Todd covers them in biology usually pretty well, and you usually get them elsewhere. And we always skip the nutrition chapter, because how many people have had nutrition? Or will have nutrition? Yeah. So covering it in chemistry kind of seems redundant. Okay, the other reaction that's on there is, let's see, which one is the silver mirror? That's toluenes, right? And if you remember, that was an aldehyde plus silver ions in this case, with a +1 charge, plus ammonia, and we got a carboxylic acid salt plus 2 silver ions, and that was our silver mirror. And so if we do that same reaction with our same carboxylic or sugar, because it's the easiest one to draw, I never have to remember where the OHs go, then we'll get the same result. Now the only difference is, last time I made a sodium salt, what type of salt do I make this time? The ammonium salt, right? So I mean, it's a carboxylic acid salt, but it's specifically it's the ammonium one. And I make 2 Ag, not plus on this side, solids. And that's our mirror. And again, our aldehyde gets oxidized. That's pretty easy to see because we gain a bond to oxygen. And there's really only one other thing kind of left in the reaction. Our silver gets reduced because it goes from silver +1 to just silver with a little 0 there, meaning it gained 1 electron, or each silver gained an electron. So learn to kind of recognize what's being oxidized and reduced in reactions. Learn to follow those charges around, because we'll be doing that in the future also. And then this is also review. You've already learned both toluenes and Fehlings-Benedict's reactions. That was actually way back in chapter 23 on aldehydes and ketones, because it's our easiest way to differentiate between an aldehyde and a ketone. Okay, so we can oxidize sugars because they have that aldehyde functional group. And what would be the opposite of oxidation then? No. So, oxidation is always paired with reduction. So we can also look at how to do reductions for sugars. So we can look at reduction reactions. And notice that what we label a reaction, whether it's oxidation or reduction, is not so much, I mean, you can't say that only an oxidation occurs, because it's always paired with a reduction. It's whether the main molecule that we care about, in this case the sugar, is oxidized or reduced. So if we do a reduction reaction, we're basically taking that aldehyde functional group, and what do we reduce aldehydes to? What? Alcohols. And so if I take my favorite molecule, D-allose, because it's so easy to draw, and we reduce it. Now, you're going to either see that written as a reduction like that, or the other reduction arrow we had was, whoops, not N, but H2, nickel, and heat, right? And we're going to reduce that then so that it now has an alcohol on this end of the molecule. And so notice that I'm kind of changing how I drew that. Maybe I should just do it that way. There, that's still a carbon then. And that's generally how I would draw it. So now we have a molecule that has lots and lots and lots of OHs on it. And then of course if this is D-allose, we change the name to etol, like that, and so this would be D-eletol. And I'm trying to remember, I had some random notes about some of these. These are sometimes called sugar alcohols, and a lot of times they'll substitute these in for regular sugars in things like diabetics, diet drinks, sugarless gums, and things like that, because your body doesn't recognize them as carbohydrates, and then you still get kind of that sweet flavor, but not sort of the same effects from it. So we've got reduction reactions. Let's see, we're going to do another easy one. We'll save the hard one for last, so let's skip that one. We did the redox test. Oh, well, you guys know these. These are easy. So these are paired reactions too. Dehydration. What's the paired with dehydration usually? And hydrolysis. And what's the difference between a dehydration and a hydrolysis? Right, which one is which? Yeah, so we'll usually see minus H2O. And for hydrolysis, we'll usually see plus H2O. Now, I've been taking to writing it on the reactant side, but a lot of books will just write that on top of the reaction arrow, okay? So be aware that just the way I show things is not the only way that you'll see things written in a book. And we're going to even take this one step, well, let's just show it the way it is. So we'll do this in the review section. So here I've got this, and I'm just making up a sugar. I don't even know which one it is. Notice I put all of those down because I'm lazy. And then if I react it with another sugar, then just for fun, we'll put all of these facing up. And I'll let you guys catch up. Maybe for review, we'll throw in some random stuff like which one's alpha and which one's beta. Let's see. Alpha is beta up, alpha down. So this is the alpha molecule, this is the beta one, right? And since I'm going to lose H2O on this, what I'm really going to do is make a glycosidic bond, right? So you guys remember that term? Really, that means that we're making an ether bond because we're reacting those alcohols together to make an ether. And then we can make a variety of glycosidic bonds. For instance, one of the ones I've noticed people got wrong on their homework a lot is everyone got used to seeing the 1,4 glycosidic bonds, but we can have, for instance, a 1,3 glycosidic bond if we want it. And so in this case, if I make a 1,3 bond in this molecule, then what I'm saying is that I take that OH, and now it's just going to be an oxygen, and it reacts with the number 3 OH, which is 1, 2, 3. So it's really reacting with this one, right? So I'm reacting these two. There's my minus H2O part. And so that means that that bond needs to be drawn to that one right there. And let's see, that OH was up, this OH was up, this OH was up, O, CH2OH, CH2OH, oxygen, and I drew all of these down. And so really this is an alpha 1,3 glycosidic bond, right? Because the first molecule is alpha. I connected the number 1 carbon with the number 3 OH, or the number 3 carbon. And notice that here, for instance, that shows is that OH had been up, right? And the reason I knew that OH was up is because I would normally be told what sugar molecule. So really what I simply did is I took a monosaccharide plus a monosaccharide and I made a disaccharide. And we've already done that before, right? So this is a review reaction in that we already know how to do it. And then of course, what would be the opposite? If I did the hydrolysis, it would simply be going in the opposite direction. So if I did this with plus H2O, then I should get my 2 starting molecules, meaning I break apart that bond in the hydrolysis. So your body is constantly doing these dehydration and these hydrolysis reactions. If it wants to store the glucose or the excess glucose in your body, it converts it to glycogen or that. And if it's a plant, the plant takes all its glucose and stores it in the form of amylose or amylopectin if it wants to store it for energy use, or it stores it as what if it wants to be structural. Aaron, did you have a question?
I'm trying to figure out how that hydrolysis works.
I mean, it literally is the reverse reaction. So you just break it apart at that ether bond or that glycosidic bond, since this is biology now, or at least biochemistry. And you would literally get the 2 starting molecules. So I mean, it literally is the exact opposite.
That, and then you end up with that.
Yep. So it just depends on which direction we're going. If we start with 2 monosaccharides, then we have to remove water. If we start with the disaccharide and break it apart, we do that. So when we're making molecules like this, I mean, this reaction is constantly happening, right? If a plant wants to grow, if it wants to, make new leaves and new structures like that, it has to make more cellulose, right? So it stitches these monosaccharides, the glucoses, together into cellulose. And then if it wants to break down something, or for instance, our body needs some glucose, a quick energy, it takes the excess glycogen that our body has stored in the liver and simply does a dehydration and breaks it right back down into glucose molecules. And then what type of bond is made simply determines what we're doing, right? One of the things I noticed people struggled with is, what's the difference between this, all other parts being the same. Oops, there's an oxygen in there, and that. Meaning all the rest of the molecules the same. I'm not going to sketch it out because I'm being lazy. But all the rest of that's the same, CH2s, OHs. What's the difference between these 2 molecules? Right, so be more specific. I mean, that's like saying, what's the difference between a boy and a girl? Well, one's a boy and one's a girl. Yeah. No. So remember, this tells me whether it's alpha or beta for the glycosidic bond, right? So that's an alpha, this would be a beta. So this is an alpha 1,4 glycosidic bond. This is a beta 1,4 glycosidic bond. Whether this one is up or down is determined by what I'm connecting together, right? Meaning in this case it's glucoses together. And whether the overall molecule is alpha or beta depends on whatever is stuck on the other side of this molecule right here. This would really determine whether the molecule is considered the alpha or the beta. So one's got an alpha 1,4 glycosidic bond, one's got a beta 1,4 glycosidic bond. So which one's cellulose and which one's starch? Boy, you guys got a lot of remembering to do. So alpha 1,4 bonds make this starch equals potatoey goodness. This makes this cellulose equals horsey goodness. Since in cows and things like that, they eat, well, they don't actually, I don't know. I mean, they eat certain types of cellulose. They can't eat, well, actually, some horses do apparently eat wood if you stick it in a wooden stall. So remember, it's small little things like this that if you look at a picture of these, you should be able to look and say, oh, well, there's something different between the bonding. One's an alpha 1,4, one's a beta 1,4. Now I know that one is starch and one is cellulose. What we're really focusing on in all of these chapters for the biology is tiny little things like that have big impacts on how something functions. And so you need to be able to recognize the tiny little changes and then understand how that leads to the bigger impacts. Okay. One last big uber one, and this is actually a series of reactions. It's called the Killiani-Fischer reaction. And you guys have heard of Fischer projections, right? Same Fischer guy. This is how the first set of carbohydrates were sort of built from scratch, meaning that, of course, you could isolate them in nature, but one of the things that people struggled with is that how many isomers of glucose are there, for instance? Glucose has 4 chirocarbons. Remember, chirochemistry is also on that test. So 4 chirocarbons means how many stereoisomers?
Oh my god, I can see the 2 and then you play on.
So 2 to the 4 is what? 2 times 2 times 2 times 2. What? 16. 16. Or 32. So 2 times 2 times 2 times 2 is 16. So there's actually 16 stereoisomers of a carbohydrate. So if you want to try to build these in lab, you're going to get a mixture eventually of 16 different compounds potentially. And so what the Killiani-Fischer reaction did is it took a molecule and allowed you to build the specific molecule you wanted. Now, technically, you really end up building 2 different molecules at each step that you have to separate out, but that's a lot better than trying to separate out all 16, right? Or something like that. So, what this is it's a series of, there's 3 reactions that form a cycle. And we've seen all 3 of these reactions before, and what these reactions really do is they make the carbohydrate 1 carbon bigger. So the idea was they started with the simplest molecule that they could kind of start with and built up all of these different molecules and then discovered, or looked at all the different isomers. So the smallest possible molecule you can have is a 3-carbon molecule like this. Actually, I shouldn't say this is the smallest you can have. This is actually 1 step in it. This is called D-glyceraldehyde. Not that you have to memorize the name, it's actually on your cheat sheet. And notice that we're already starting with the D isomer, right? And so really, we've already gotten rid of, and now we would only have 8 more stereoisomers that we could make, right? Because 8 of them are Ds and 8 of them are L's, right? And so we react that with HCN, and we're going to get 2 different products from this. So this is where that split occurs. And then after this, everything is simply redrawing the molecules over and over again. So what do you guys remember HCN was? So if I had an aldehyde plus HCN, what did I make? Actually, maybe I'll go like this. Yeah, this was what we called a cyanohydrin. And what happened is, if I had an aldehyde like this, right, then I got a molecule that looked like this, where I got an OH here and a carbon to a triple bond here, right?
Is that aldehyde plus HCl or
HCN. Oh, this second one should be an N. I just apparently got distracted while finishing my N. So notice that this is a new OH group, right? And so if I take this molecule, what we're saying is that this aldehyde carbon right here now forms a new OH group. And on the top of the molecule, I have a carbon triple bonded to a nitrogen. That's kind of an ugly looking triple bond. And the part that makes it a little harder is that, of course, that new carbon is chiral, and so it really actually forms two different products, meaning that 50% of the time that new OH is up or to the left, and 50% of the time it's to the right. And see, this was actually chiral in chapter 23, but since we didn't care about chiral chemistry in chapter 23, we never bothered pointing out that you'd really get two products when you make that. And chemically speaking, you could care less which of the two products you make. Chemically, they behave the same way. Biologically, we know that they behave very differently. So that first step actually creates two products, and then every step after that is showing or doing another one. So this next one is a hydrolysis reaction. We're adding H2O to the molecule, so plus H2O. Now, this is again where, depending upon the book you look at, that plus H2O might be on its own line, meaning it might be shown as a reactant, or that plus H2O might be shown on the reaction arrow. And then that H plus there is simply saying that we need to do it in acidic conditions, right? And so when we saw this, so this next step, step 2, is hydrolysis. Or basically we're adding plus H2O to the molecule. Actually, it's not hydrolysis. Why did I say hydrolysis? Should be an addition reaction because we're adding the H2O. I don't know why I said that. And what happens if we take a nitrile plus H2O plus, we did it with HCl, meaning we had a very specific reaction. What happened to the nitrile? No, that is the nitrile, right? So what happened to it?
Oh, it broke that bond and then it went to HCl. Where did HCl come from?
Well, okay, so remember I said that like a lot of times most books will show it with just that H plus there. We did it very specifically way back in chapter, I'm going to guess 24. No, wait. Nitriles and stuff were in chapter 25. What happened when we did an addition reaction with H2O and a nitrile? Yeah, we broke we broke the triple bond and made a carboxylic acid plus. Now, see, when we did it in the chemistry chapters, we made an amine salt, or in this case, we made ammonium chloride, right? In sugar chemistry or biochemistry, we sometimes ignore that extra product, and so we're simply changing that to a carboxylic acid. And then really we should write, plus NH4Cl, but again, in the carbohydrate chapter, we don't care about that, right? Just like, depending upon the book you look at, especially once they start getting into, biological reactions, they leave off half the reaction sometimes. As a chemist, I'd like to know that I also make ammonium chloride. It makes the reaction nice and balanced, everyone's happy, things like that, but, they don't bother doing that. And then the last step, the part that allows us to make this cyclic, is by reacting it with an amalgam of sodium and mercury. Now, this is how biologists did it. This is how they really did it. But for us, what we'll realize is that if I take a carboxylic acid and I reduce it, what do I get? Yeah, we get an aldehyde. So, you know, when we did it, we looked at a reaction like this, where we'd say like this, OH, H2, Ni, and heat, and we simply made the aldehyde. And plus H2O technically. But this just turns us back into an aldehyde on the top. So if you have the idea of, you know, the organic chemistry kind of in the back of your mind, and you tell yourself, oh, this is just a cyanohydrin reaction followed by an addition reaction followed by a reduction reaction, then you can remember what happens. If you want to simply remember that it gets turned into a nitrile to a carboxylic acid back to an aldehyde, that's another way to remember it, right? And so the key step really in this reaction are kind of the fact that, you know, here we add one carbon, right? Meaning we went from something that started with 3 carbons to now our molecules have 4 carbons. And then all the steps after that are simply to return our nitrile back to a carboxylic acid, and our nitrile back to an aldehyde. And once we're at an aldehyde, then we can just rinse and repeat. That's like laundry. That should be something everyone's familiar with doing.
Is that 4 carbons? Half more, half more.
Yes, because 3 plus 1 is?
7.
I know, it's early. It's a Monday, spring break. Everyone's IQ probably dropped about 50 points. Because I really do believe you get stupider if you're not constantly learning. I think they've done studies that show that old people, like Alzheimer's and various things like that, seem to take longer to onset if your mind is continually active. That just like exercising muscles, you can exercise your brain. So if you don't exercise your brain, you get stupider. Just like if you don't exercise your muscles, you get weaker and maybe fatter, maybe not. You can be skinny and weak too. Yeah, I don't know. I had this idea over spring break that I've been wanting to, I made some chocolate chip cookies, which reminds me, they're sitting in my office. But anyway, I was trying to decide if it was really worth calculating how many calories was in a chocolate chip cookie that I intend to make, or if I would be just depressed knowing that. Because I ate out last night in Vernal at KFC. Ugh. Yeah, I know. I don't know why I did that.
Have you ate that Mexican place?
Which one?
It's like hidden out there, but it is so good.
Oh,
Yeah.
heading up towards the gorge.
Yeah, I think so. It's really good.
Yep. One of those little hidden gems. So anyway, just looking at the menu items, it was like, wow, if I ordered that, that's 1,200 calories. That's all the food I really should eat in a day if I'm not doing much.
That place should be fun.
Yeah, I eat at KFC about once a year, and then after I'm done with the pile of napkins that have all my grease that I had to wipe off my fingers in between eating it, then I'm like, this is why I only eat here once a year. But boy, it tastes pretty good sometimes. So the idea is that now I can take that 4-carbon molecule, and if I wanted to, depending upon which one I chose, I could start all over, right? So eventually this molecule, if I did a cycle, one Kiliani-Fisher cycle. Hey, one Kiliani-Fisher cycle. that's just one of those weird coincidences in life. So 1 KFC later, then I would have one of two molecules, right? I would have one with 3 OHs like this. Or I would have the one where that new carbon I added is on the, or that new chiral carbon is on the last side. And so, and I don't remember which version of the cheat sheet I gave you guys, if I gave you this one or if I gave you just the one that listed. But you can see where if I take the aldehyde here, I make 2 families, and then I break it apart and I make 2 different ones and I break 2 more. And so each cycle, I add another set of isomers on there. And so if I start with diglyceraldehyde and I make it all the way up to an aldohexose, meaning I make it to 6 carbons, so this is 4 carbons, this is now 5 carbons, right? See, this would break apart into 2. This would eventually break apart into 2, you know, and then I would get my 6 carbon ones. You can see where I would get 8, right? And then, you know, so on and so forth. And so the Kiliani-Fisher reaction was how they first made all 16 stereoisomers of a carbohydrate. And a certain part of me says that that's pretty impressive. And I'm trying to remember, I should look in my notes and see if I have it written down somewhere. I'm pretty sure he got a Nobel Prize for doing that. But I could be wrong. I don't even see where it is in my notes. Right, so that's the idea, is that each time you go through a cycle of this reaction, you get 2 different products, right? You get a 50-50 mix. So, you know, I guess I could show this one right here. That goes to either this or this, right? And so we keep getting it bigger and bigger. Man, I don't even see where Kiliani-Fisher is in my notes. That's okay. I wrote these notes and then realized that really I just do it in whatever order I feel like that day, and so it doesn't really matter where stuff is sometimes. But Fisher projection. Carbohydrates. It's about all that the reaction is truly useful for. It does show you, though, that, you know, way back when, they had to be really smart when they did chemistry, and so they had to really sort of do things. Man, I don't even see where that is written. I was kind of curious. I'm pretty sure he got a Nobel Prize for it, but oh well. All that extra random stuff in there. Did I say he got a Nobel Prize here? No. And I think that's it for this chapter. What this really means is that if we look at Monday, Tuesday, Wednesday, Thursday, Friday, so that means on Tuesday, let's say homework 27E is due. And really, technically, on last week, Friday, everything from homework from chapter 26 was due well before then, and homework 27A, B was due way before then. And technically, on that day, only homework 27 C and D were due. So, you know, for people that are still working on all of that, ouch. So we're going to do homework 27E is due tomorrow. We're also going to do lab, whatever number it is on carbohydrates. I forget the number. If I was smart, I'd call it lab 27 since it goes with chapter 27. It may be lab 27 in your thing. I don't know. So make sure you do the pre-lab. It's actually 26. Oh, are we in chapter 26? No, we're in chapter 27. Oh, I don't know. I just, when I was numbering them, I really just random. The order I wrote them in is the order that they were numbered in for the most part. So Wednesday we're going to start chapter 27. Thursday we're going to have lab, the second part, and then Friday I'm thinking there's going to be a test on chapter 26 and 27. I'm 20, sorry. 20, yeah, 26 and 20. Oh, start chapter 28 on lipids. Sorry, chapter 26, chapter 27. I get confused with all the numbers after a while. You know, I could keep track in like numbers 1 through 16 in my book, but I always notice, like, I know what chapter 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 is. And And then towards the second half of every semester, the numbers start to get mixed up in my head and I forget which stuff is in which chapter. And then I think that looks good. What's my calendar say? Yeah, that's a good day for a test. And that's it for me. What I'm going to recommend is that any homework I gave you, start going through that. Start looking at the handouts that are on the web for studying for chapters 26 and 27. You know, start asking questions. A lot of that was a long time ago. Some people told me what they did is they ended up redoing their homeworks because they're like, well, I don't remember them anyway. Because I don't know about you guys, but I remember this stuff now because, oops, I forgot to turn this off.